By the end of this lesson, we'll be able to boil down to a single resistor. Here we've got a combination of series and parallel. If we pulled out light bulb A, that's going to cause B and C to go out. We can't do this. This is illegal because we've got current going two different directions in one wire. That is the rule you can't do. So if you pull out B, A and C still stay on. If you pulled out C, A and B still stay on. So let's say all three of those have 2 ohm resistors. Okay. So what I'm going to do is I'm going to take this in steps. I know that A affects everything. That's too big. I want to deal with things in small bites. Okay. So B stays on. Sorry, if I pull out B, C stays on. If I pull out C, B stays on. So from here, I can discern that B and C are wired parallel with respect to each other. Current has a choice to go this way or that way. So I'm going to combine those two resistors in parallel. So we got 1 over R is equal to 1 over 2 plus 1 over 2. That ends up being 2 over 2, which is equal to 1 over 1. So the total resistance is 1 of that. So then I'm going to redraw my circuit. Okay. This is the part that you're not going to like. You get over it, deal with it, because tomorrow it's going to be really beneficial. So this is light bulb A. This is going to be BC, the combination of the two. So this is still 2 ohms. This now is 1 ohm. We've combined these together to give us BC. Does that strategy make sense? Now, if I pull out light bulb A, BC goes out. If I pulled out BC, A goes out. So I can conclude they affect each other and only each other. Therefore, these two are in series. The total resistance for series is, you just add them up. So the total resistance of A, B, C is 3 ohms. 3 ohms is the equivalent resistance of this circuit. You good with that? Questions there? Okay. This is similar to circuit 7. I pulled out A. C goes out. Okay. I cannot do this. That's illegal. Okay. If I pulled out B, A and C still stay on. If I pulled out C, tell your neighbor what other light bulbs go out. Correct answer is A also goes out. This does not count. It has to be brought back to negative. Okay? Simply tagging it doesn't turn it on. It has to go through and back to negative. You can't reverse the current here. Okay. So if all these light bulbs had 2 ohms of resistance, B doesn't affect anything. A affects C, C affects A. You're like, oh, they affect each other and only each other. So my first step is to say that A and C are wired in series. So I'm going to redraw that. This is AC, has a total resistance of 4 ohms because I just add 2 plus 2. This is B, has a resistance of 2 ohms. If I pulled out B, AC stays on. If I pulled out AC, B stays on. Current has a choice here. So B, AC are wired in parallel. So I got 1 over R, bless you, is equal to 1 over 4 plus 1 over 2. That gives me 3/4. So R is equal to 4/3. Redraw. It's ABC, 4/3 ohms. The equivalent resistance of that circuit is 4/3 ohms. Good with that? Questions there? Let's do something a little more complicated. Oh, yeah. That more complicated. Okay. I'm going to start taking out one light bulb at a time. If I took out A, what other light bulbs go out? Tell your neighbor. Correct answer is everything. Okay. Okay. If I took out B, tell your neighbor what other light bulbs go out. Correct answer is D. I can't do this. If I took out C, what other light bulbs go out? Everything still stays on. If I took out D, what other light bulb goes out? ACE stays on, but this is illegal. They go like, gotcha. Okay, it has to flow through and back home. So B goes out. If I took out E, everything goes out. This is not a complete circuit. Good with that? Okay. So if I took out 4, that affects everything. 5 affects everything. Stay away from that until the end. That affects everything. Okay. If I take out 6, doesn't affect anything. If I take out 2, that affects 1. If I take out 1, that affects 2. So that's like, hey, these two, 1 and 2, they affect each other and only each other. Okay, they're dependent on each other. So these two are wired in series. So I'm going to add those together. Please redraw this. Every level. It's really, really, really going to be beneficial for tomorrow's lesson. Okay. So this became that. Okay. 4, everything goes out. 5, everything goes out. Don't touch those. 6, everything stays on. 3, everything stays on. Here the current has a choice. So 3 and 6 are wired in parallel. 1 over R is equal to 1 over 6 plus 1 over 3. Gives me 3, 6, 1/2. R is equal to 2 ohms.
How do you know they're parallel?
Great question.
Oh, well, I just wasn't listening.
Okay. There was, the current had a choice. If I took 6 out, it doesn't affect 3. If I took 3 out, it doesn't affect 6. So if they don't affect each other and nothing else is affected by those, then we can lump those in parallel with each other. Redraw. Okay, 4, 2, 5. If I pull out 4, everything goes out. If I pull out 2, everything goes out. Pull out 5, everything goes out. So based off of that, I can say all 3 of these are wired in series. Total resistance, 11 ohms. JP. In one, yeah, in one. Boil it down to one resistor. What's the total resistance of this circuit? Okay, so this is step 1. Today is step 1 in how you deal with combination circuits. Tomorrow we'll learn step 2. Okay. Good with that? Okay. Here's another example. I had this question. I remember this question from high school. If you pulled out A, what other light bulbs go out? Tell your neighbor. Okay, when I was in high school, I thought B and C stayed on if you took out A. Because I thought this. Tell your neighbor where my error was. Okay. Right here, current can't go two different ways in one wire. Okay. B and C go out if you pull out A. Okay. Okay. If I pulled out B, what other light bulbs go out? None. They all stay on. Okay. If I pulled out C, same consequence. Everything stays on. Nothing goes out. If I pulled out D, what else goes out? E goes out. If I pulled out E, what goes out? D. How are we doing with that? This idea. Okay. So put in some numbers to it. Okay. The order at which you simplify makes a difference. Okay. So 5, you take that out, that affects 4. 4 affects 5. So 4 and 5 affect each other and only each other. That's a good place to start. Okay. So these two are wired in series. Redraw. Okay, so I get 9 ohms. Good with that? Okay. Here's a popular error. If I pull out 1, nothing happens. If I pull out 2, nothing happens. If I pull out 9, nothing happens. Oh. 1, 2, and 9, those must be in parallel. Here's why that's not good. Why you would not want to do that. Because if you pull out 3, that only affects 1 and 2. It does not affect 9. So there needs to be some simplification going on here before I bring 9 into the picture. Does that make sense? Okay. If you, as you're unscrewing light bulbs, if you've got something that affects like a couple of them and not affect another one, that's not a good grouping. Like don't group 1, 2, and 9. We first need to deal with this. Okay. Now we unscrew 1, 2 stays on, 2, 1 stays on. Unscrew 3, both of these go out. So I'm going to group 1 and 2 in parallel. Okay, so 1 over 1 plus 1 over 2 gives me 3 halves. So R is equal to 2/3. Redraw. Okay. If I pull out 3, 2/3 goes out. If I pull out 2/3, 3 goes out. 9, nothing happens. So I'm like, These two are wired in series. So this is 3 2/3, which is also equal to 11 11/3. That's 9. Now, you pull out 9, nothing happens. Pull out 11/3, nothing happens. So these two are wired in parallel. So 1 over R is equal to, check this, 3/11. That makes sense. Plus 1 over 9, that is equal to 0.38. Repeating. Whether you use decimals or fractions, I don't care. I kind of prefer decimals, but whatever. When you find the reciprocal of that, you find that to be 2.6 ohms. Redraw 2.6 ohms. Okay. When I was in your shoes, this came as, for me personally, this is how I learned. This came as a relief after static electricity. It was like, oh, this is like a puzzle. Like I can do, okay. Like if you can crack the puzzle, if you do your steps, these aren't bad. You just got to figure out the pattern. Okay. So you got a worksheet tonight, got a lab quiz tomorrow, test Wednesday. Okay.